Hello, welcome back. This is the third installment of Thermodynamics. And this, if you got your slides, this is the part 2 of the slides, but this is our third installment. In this installment, what we're going to look at is changes in internal energy and some pressure volume work things. So, internal energy, and now we're going to be talking about E rather than H. Okay, internal energy is all the energy that's in a substance. You may recall that you have potential energy stored in your bonds between some of your molecules and things like that. And depending on what that molecule is, like ATP, if you've ever had biology, is a very high energy bond between the adenosine and the phosphate. The change in internal energy is just like we've seen before, the energy of the products minus the energy of the reactants. It's the amount absorbed by the system plus the amount of work done on the system. So the way we write that mathematically, let me get my pen situated here. The way we get that oriented mathematically is that delta E is going to be equal to Q plus W. Q is heat, like we've already seen, and then W is the amount of work done on the system. Okay, so as I said, Q is heat energy, W is the work energy, and that is what? Force times distance. The sign conventions of this is that the heat and work that's put into the system, okay, done to it, absorbed into it, anything into the system is going to be positive. And anything leaving the system, going out, evolving, released, is going to be negative. Okay, so work done on the system is positive, work done by the system or work that is released from the system or whatever is negative. So when we look at changes in internal energy, this is really just a very basic mathematical thing. The change in energy of the system, of the internal energy, I should say, is going to be the energy when we get done minus the energy when we started. It's also equal to, as we know, Q plus W, the amount of heat plus the amount of work done on the system. So in this particular problem, we have 1200 joules of heat, and they're added to system in energy state E1, and the system does 800 joules of work on the surroundings. Okay, so you've got to interpret how this is written. So the delta E, we've added 1200 joules. Okay, so 1200 joules. And we've done, and so we're looking at this part, right? That's the heat, that's the amount of heat added. And it does 800 joules of work on the surroundings. Okay, so if it's doing work on the surroundings, that means that it's being done by the system. So that's actually going to be a negative number of joules of work. Okay, so the delta E for that system is going to be 1200 minus the 800 or plus 400 joules. So that's going to be the amount of work done by the system. Okay? What would be the energy change of the surroundings? Okay, well, we know that the total is, they're going to have to be equal, right? So if you've got plus 400 joules on the system, then what's on the surrounding is got to be a minus 400 joules. Because if you end up with 400 joules of work by the system, it had to come from somewhere. So the surroundings had to lose the 400 joules. Okay, so that's that first law of thermodynamics that we looked at when we first got into this chapter. So third, what's the energy of the system in that new state? If we're now in this new state and we've done this work on the system, and we said initially that the internal energy, the change in internal energy, was what it was like now minus what it was like at the beginning. And so if we rearrange this to solve for what it's like now, E sub 2 would equal what? E sub 1 plus delta E. What did I do? I moved it over and changed the sign. Okay, and so E sub 2 is going to be E sub 1, because we didn't know what E sub 1 was, plus 400 joules. Okay, because this is the system, delta E of the system. Okay, so E sub 2 minus E sub 1 will give us that difference. Does that make sense? Okay, so changes in internal energy are just basically based on what's happening, how much work we're doing with the system or on the system, or how much heat is leaving or coming back in. Okay, so one thing that we talk about in systems a lot is pressure volume work. The first work that was done on this was done with pistons, and so we're thinking about pistons and pressure and gases and things, you know, pistons like in your car. So the amount of work that can be done, work is defined as the force times the distance. Okay, it also has other equalities. It's also the negative of the pressure times the change in volume. Remember, think about how we're doing a piston up and down, where P is the external pressure and delta V is the volume before and after you've done the work, before and after you've either pushed or released that piston. So work is equal to negative P times delta V. It's also equal to the negative of delta N, number of moles, times RT, if you remember that from your ideal gas law. That's where that came from. Okay, so delta N is the change in the number of moles of gas. So if you change how much gas you're putting in there, it's going to be related by the ideal gas constant R and whatever the temperature is at that time. Now, this is assuming we're not changing other things, okay? So if we have constant volume, the delta V is going to be 0 because you have the same volume that you end up with that you started with. Therefore, work W would be 0. Delta E would be equal to Q plus W. So if work is 0 at constant volume, then delta E at constant volume would be equal to the heat at constant volume. Solids and liquids have a delta V of 0 because they are not compressible. Okay, but if you recall, our gases are compressible. So our gases will change volume when we push on them like that. Okay? All right, so delta H, there's our old buddy enthalpy, is equal to heat at constant pressure. That's what we did before. Okay? Delta H is also equal to the change in internal energy plus P delta V if P and T are constant, or it's equal to delta E plus delta N RT, okay, if it's not constant. So the difference between the change in enthalpy, delta H, and the change in internal energy, delta E, is how much work the system does, which is P delta V. How hard you have to push to change the volume. Now, if those two things are zero, then delta H equals delta E. So if you keep enough things constant, the enthalpy change and the change in internal energy can be the same. All right, so we noted way back that the delta H0 value for the combustion of pentane was a negative 3523 kilojoules. Okay, so this is the delta H0 for pentane. And the combustion of 1 mole of pentane at constant pressure releases 3523 kilojoules of heat. Okay, that's just another way of saying that it's a delta H0 of minus 3523. What are the values of the work term and delta E for this reaction? Okay, so we have to determine the work done by the reaction. Now, I know I kind of gave you a bunch of different little things. You have to kind of use what you need of those that I was kind of throwing out there. So our here is our chemical equation, and it's balanced. We have pentane plus 8 O2 plus 5 moles of CO2, or gives us 5 moles of CO2 and 6 moles of H2O. And it told us that our delta H0 was equal to a negative 3523 kilojoules. Or, what else did it say? We release 3523 kilojoules. Okay, that's just two different ways of saying that, right? Okay, so to determine how much work is done on this system, we've got to look and see that we know that if we're doing this and this H0 is that number, this H0 tells us that what? It's the standard condition, right? It's the standard condition. So if I know it's the standard condition, what I also know is that T is equal to what? 298 K. Because that's the definition of standard, right? 25 degrees C or 298 K. So in this case, the amount of work done is going to be equal to minus P delta V, or minus delta N times RT. Delta N of the gas, remember, because if it's a liquid, we don't care. It's only gases that can do this, right? Okay, the delta N of the gases is going to be 5 products minus reactants. It's going to be 5 minus 8. It's going to equal a negative 3 moles. Okay, that's the change in moles. So work is equal to the negative delta N times R times T. So, do you remember, if you recall what R is, R, which is the ideal constant, remember we're now working in joules. Some of you might remember that 0.083 number, liter atmospheres. This one, we use the one in joules because we're talking about energy. So it's going to be in joules per mole K. All right, and the numerical value for that is 8.314. All right, so once we know our change in moles, then the work is equal to the negative of the minus 3 moles times 8.314 joules per mole K. What else I got to get rid of? K times 298 K. We know that because it's at standard temperatures, right? Okay, so that will come out to 7433 joules or 7.433 kilojoules. Either of those would be correct. So that's the amount of work done by that reaction. Remember, we're doing combustion. So if you think about combustion in an automobile engine and you're burning it and it's driving a piston, that's the work we're doing, okay? And so it's the change in moles times the ideal law gas constant times the temperature that you're running it at, which in this case was 25 degrees C or 298. Now, that's the work term, okay? Also wanted to know what the change in internal energy is for this reaction. Okay, so the delta E for the reaction is going to be, delta E is equal to delta H minus P delta V. Okay, now we already know that P delta V is equal to 7.433 kilojoules. That was the work we just calculated on the previous screen. Right? Yep. Okay, so that was the minus P delta V. That was 7.433. So P delta V is the opposite of that, which is a negative 7.433 kilojoules. So delta E is equal to delta H, which we know was from the problem, which is a minus 3523 kilojoules per mole minus 7.433 kilojoules. That's actually, we've already taken that out. So this was the number of work that we did in kilojoules. This was the total kilojoules. So if you've got, this thing keeps writing over that. So 3523 minus a negative 7.433 is going to give you 35, that was negative, 3516 kilojoules. Okay? So that's the delta E. We calculated this first, okay? That was the work done. That was W, okay, W. And so the it's the total energy of the system minus the work done gives you the change in internal energy. That's all we were doing, okay? Clear as mud, right? Okay, so spontaneity, just like, like, have you ever heard anybody want you to be spontaneous? They want you to, just like kick off your shoes and go jump in the lake or whatever and, be spontaneous. So spontaneous really means that something will happen without any energy being put into it. That's what it means basically, that it's favored. over something else. It does not mean how fast something goes. It means the favorability of something happening. Okay, so a spontaneous reaction is a reaction where the products are going to be more stable than the reactants. So a spontaneous reaction means that it's going to happen because you want to be more stable, so you're going to go more to that product side than the reactant side. Non-spontaneous reactions are going to be where the reactants are more stable than the products. And so if you want to get them to do something, you're going to have to probably put energy into it. Okay? So you're going to have to make them do something because they're already stable. There are two parts for spontaneity as far as whether a reaction is going to be spontaneous or not. Heat and disorder. So we've already looked at the enthalpy, the delta H. The other is entropy, and entropy is randomness or disorder. And spontaneity is going to be favored by a negative delta H, okay, because that means it's going to be exothermic and give off heat, so it doesn't need heat put in, and positive delta S, because that means that it is random. Okay, so its entropy is high. Okay, now, I know it's crazy at first. It'll be okay. The second law of thermodynamics states that in spontaneous changes, the universe tends towards a state of greater disorder. Greater disorder. Okay, so if we want to go to a state of greater disorder, think about the differences between solids, liquids, and gases. In solids, liquids, and gases, if you look at the way those molecules are put together, in a solid, they're very, very symmetrical and lined up and, in this really good order. So there's very little randomness or disorder to those. In a liquid, there's a little less structure to them, and they're a little bit farther apart and a little bit more likely to bounce into each other. And then a gas is going to be the most random of all. So it has the most randomness or the highest entropy. So entropy is a measure of the disorder or randomness of a system. The greater the disorder, the higher the entropy is. Okay? So solids have the lowest S, and gases have the highest S, or randomness in the system. So, I don't know what's going on with that. Okay. All right, so from the second law of thermodynamics, for all spontaneous reactions to occur, the entropy of the universe is going to equal the entropy of the system plus the entropy of the surroundings. And these two things, in order for it to be spontaneous, need to be greater than zero. And we've already seen greater than zero means what? Positive. So for a reaction to occur, the delta S needs to be positive. And we already said the delta H needs to be negative. Okay? So just remember they're the opposites. H and S are both opposites. The third law of thermodynamics says the entropy of a pure perfect crystalline solid at 0 K is 0. So there is no randomness or movement, really, of a solid at absolute 0, 0 K. Now, of course, we don't run reactions at 0 K, do we? No. We run reactions at 25 degrees usually in our labs, and in other labs, you'll see kind of the same thing. So the entropy at 298 is our standard entropy. Okay, so all the values at standard entropy are going to be positive, and they're going to be derived from math involved in that third law of thermodynamics. The change in entropy of a reaction, just like Hess's law before, is the sum of all the entropy of the products minus the sum of all the entropy of the reactants in joules over K times mole. The entropies are measured and tabulated where? In our old buddy Appendix K, okay? And it will be listed as S0 at 298, okay? So we have H's, and now we have S's in Appendix K, and they're just in different columns for those same materials. And remember, just like we saw before, elements have an S0 value. Unlike, I should say, what we saw before, elements do have a numerical value for S, for their randomness. All right, so calculate the entropy change for the following reaction. Remember, this is just like we did the enthalpy change, except we're using the S values instead. Let me see if I give you this reaction or if I need to. Yeah, okay. All right, so, oh wait, no I didn't. Let me go back. Okay, so the reaction that we're going to do is 2NO2, just going back and forth, to N2O. Okay, and they're both gases. Oh, 4. I was looking at that because it wasn't balanced. Okay, yeah, N2O4. All right, that makes more sense. Okay, so the delta S0 of the reaction is going to be equal to the sum of all of the entropies times the coefficient of the products minus the sum of all the coefficient times the entropy, the standard entropy of the reactants. Okay? It's the same exact thing we did before. So in this case, we only have one thing, right? So it's going to be the standard entropy of the N2O4 minus the standard entropy of the N2O, but we got two of those, so we got to remember to use the coefficient. So when we put them in there from our Hess's summation law, we'll have 304.2. Where did I get that number? Appendix K. So N2O4, if you look at that, remember S's are always positive. Okay, so it's going to be A plus 304.2, and N02 is going to be a plus 240.0, okay, from Appendix K, just so you don't get confused. So 304.2 joules over mole K minus 2 times, because there's two of them, 240.0 joules per mole K. All right, and that's going to give us minus 175.8 joules over mole K. Oh, and it's going to be negative, right? Because this is going to end up being like minus 480 because we're subtracting, and this was 304.2. So it gives us a negative 175.8. All right, and or if we had it in kilojoules, we could do a minus 0.1758. Okay, and again, it just depends on what you're going to do with that number as to what you're, if you want it in joules or kilojoules. Usually if you're working it for me, if it's on a test, it's going to give you options. so you won't have to know. You'll figure out whether it needs to be in joules or kilojoules, because you'll have multiple choice answers. If it's on AL, then you got to be careful, because you just got to make sure you're giving AL what it wants sometimes. Okay, so the next question is calculate the delta S at 298, the standard molar entropy for the reaction of this. Okay, so we've got 3 moles of NO, 1 mole of N2O. Oh, don't do that. It's going crazy on me. Sorry. Okay, and then 1 mole of this. Okay. All right, I will win, so don't worry. Okay, so this time we have 3 moles, 1 mole, 1 mole. All right. Again, if you hadn't figured this out, these are all gases, so they're all gonna play. All right. So the delta S0 at 298 is going to equal the products. So N2O. Let's see. N2O is 240, because we've already done that one, hadn't we? No, I guess not. No, that's NO2. NO2 is 240. And N2O is 219.7. Again, these are from where? Appendix K. And then NO is 210.4. Okay, and those are all joules over mole K, remember. Okay, all right, so your delta S0, 298 is going to be equal to the S of N2O plus the S of NO2 products minus 3 times the S of NO, right? Okay, so our delta S0 at 298 is going to be equal to 219.7 plus 240 minus 3 times 210.4, and those are all in joules over mole K, and that's going to equal negative again 1724 kilojoules per mole, or 172.4 joules over mole. Okay. 172.4 or 0.1724. Okay? So that's entropy. Now, what we're using this for is, remember that entropy will increase as you go from a solid to a liquid to a gas. It will decrease as you go back the other way, from a gas to a liquid to a solid. So we can predict phase changes with this. Temperature changes as you increase T, your delta S will increase. Okay? So as you increase, and if you think about it, as you heat it up, your molecules are going to get more random, right? That makes sense. As you increase volume, you also increase delta S because you give it more room to bounce around in. Remember, we're talking about gases typically. Mixing substances increases delta S. Increasing the number of particles increases delta S. And increasing the number of moles increases the delta S. More things to bounce into, I guess. Okay, so, but remember, if it's going to be spontaneous, the delta S should be positive, the delta H should be negative. Should be, right? Doesn't always work out that way, but that's what we kind of hope. All right, and that's it for this section of thermodynamics. Please meet me back and we will talk about Gibbs free energy.